Welcome back everyone. Today we are diving deep into networking appliances, applications and functions, an essential topic for your Comptia Network Plus studies. We are going to compare physical and virtual implementations of key devices, explore critical network application and break down some foundations. And this will cover part 1.2, compare and contrast networking appliances, applications and functions, part from Comptia Network Plus objectives. Let's get technical and unpack these components step by step. Physical and virtual appliances. Networking appliances are specialized devices that perform critical tasks in a network. They can be physical hardware or virtualized software running on general-purpose servers or cloud platforms. And both have their strengths: physical for raw power and reliability, and virtual for scalability and cost efficiency. Let's examine the key players. Router. A router is a gateway between networks, forwarding packets based on IP addressing. Physically, the router is a standalone device with multiple interfaces: Sync WAN or wide area network and LAN or local area network ports, running routing protocols like OSPF or BGP to determine the best path. Routers maintain a routing table, update dynamically or statically to direct traffic. Virtual routers, often deployed in cloud environments like AWS or VMware, replicate this functionality using software-defined networking or SDN. They are ideal for dynamic scaling, but may lack the dedicated processing power of hardware for high throughput scenarios. Now let's discuss switches. Switches operate at layer 2 of the OSI model, using MAC addresses for forwarding frames within a single network. A physical switch is a multi-port device with ASICs, application-specific integrated circuits for lightning-fast switching. Switch builds a MAC address table through ARP, or Address Resolution Protocol, to map devices to ports. Virtual switches, common in hypervisors like VMware, vSphere or Hyper-V, connect virtual machines with a host, mimicking the same bridging behavior. They integrate with virtual NICs and can segment traffic with VLANs, though they rely on the host's CPU, which can be bottleneck under heavy load. Now let's discuss firewall. Firewall enforces security by filtering traffic based on predefined rules: sync source and destination IP, port numbers or protocols. A physical firewall like Cisco ACA uses dedicated hardware for stateful packet inspection, tracking connection states to allow or deny traffic. Virtual firewalls, such as those in Microsoft Azure or Palo Alto's VM series, run on virtualized platforms, offering the same packet filtering and NAT capabilities. They are highly configurable but depend on the underlying host's resources, which can impact performance in high-traffic environments. And now let's discuss intrusion detection systems (IDS) and intrusion prevention systems (IPS). These security tools monitor and respond to threats. An IDS, or intrusion detection system like Snort, passively analyzes traffic against signature databases or anomaly patterns, logging alerts for suspicious activity, say a buffer overflow attempts. An IPS, or intrusion prevention system, on the other side, goes further, actively dropping malicious packets inline. Physically, they are often standalone appliances with deep packet inspection capabilities. Virtually, they are integrated into the next-gen or next-generation firewalls or cloud security suites, leveraging real-time threat intelligence. The trade-off: virtual IDS and IPS systems can scale with demand but may introduce latency compared to hardware-accelerated versions. Load balancer. Load balancers distribute incoming traffic across multiple servers to optimize resource use and ensure availability. A physical load balancer like an F5 big-IP uses algorithms like round-robin, least connections, or IP hash to assign requests. Virtual load balancers such as Proxy or cloud-native options like AWS ELB perform the same Layer 4 or Layer 7 balancing, adding flexibility for dynamic workloads. They are great for auto-scaling but may not match the raw throughput of dedicated hardware in enterprise settings. Proxies. Proxies act as intermediaries between clients and servers, handling requests and responses. Forward proxy hides client identities, caching content to reduce bandwidth. A reverse proxy, often used for load balancing or security, sits in front of servers. Physical proxies offer low latency caching and filtering, while virtual proxies excel in distributed environments, supporting features like SSL termination or rate limiting. Network Attached Storage or NAS and Storage Area Network (SAN). NAS provides file-level storage over standard Ethernet network using protocols like NFS or SMB. A physical NAS box like Synology unit include RAID for redundancy and simple interface for sharing files. SAN or Storage Area Network delivers block-level storage over dedicated high-speed network, often fiber channel, and is ideal for databases or virtualization. Physical SANs use storage arrays, wireless access point or AP and controller. An access point extends wired networks wirelessly using 802.11 standard like Wi-Fi 6. A physical AP or physical access points broadcasts SSIDs, manages encryptions like VPA3 and handles client connections with QoS or quality of service for bandwidth allocation. Controllers coordinate multiple APs or multiple access points, centralizing configuration, channel selection, power levels, roaming handoffs. Virtual controllers, often software based in enterprise VLAN solutions, scale easily but require robust backend infrastructure to avoid single points of failure. Applications. Next, let's shift to applications, software solutions enhancing network functionality. A prime example is Content Delivery Network or CDN. CDNs like Akamai or Cloudflare use a distributed network of edge servers to cache content, web pages, videos, images. They rely on DNS-based global load balancing to route requests to the nearest node, reducing latency and offloading origin servers. CDNs also mitigate DDoS attacks with traffic scrubbing, making them a hybrid of performance and security. Unlike appliances, they are not tied to a single device but operate as managed service. Finally, networking functions, the processes that optimize and secure traffic flow. Virtual Private Network or VPN. A VPN encrypts traffic over an untrusted network like the internet using protocols such as IPsec or OpenVPN. It establishes a tunnel with ESP for encryption and AG for authentication between endpoints, ensuring confidentiality and integrity. And VPNs are often implemented on routers or firewalls. VPNs can be site-to-site for branch offices or remote access for users, with virtual instances scaling via cloud gateways. Quality of service or QoS. Quality of service manages bandwidth to prioritize critical traffic. Sync VoIP over bulk downloads. It uses techniques like traffic classification, edge-weighted fair queuing, and shaping to enforce policies. Configured on switches or routers, QoS or quality of service marks packets with DSCP values, ensuring low latency for real-time apps. It is a function, not a device, but it is vital for performance and congested networks. TTL or time to live. TTL prevents routing loops by setting up a hop limit on IP packets. Each router decrements the TTL value starting at, say, 64 and discards the packet when it hits 0, sending an ICMP time-exceeded message. It is a built-in functionality of the IP protocol, enforced by all routing devices, ensuring efficient network operation.